This is a PowerPoint water heater controller. It's based on an LM358, one of the most common jelly bean op amps. It's more than enough to drive a FET. And what makes this very simple is we use a 120 volt DIN rail mount power supply that's rated for 12 volts, 1.2 amps, 1.5 amps, I think. I'm not sure what it is. But the feature about this is it has a pot on the surface that you can adjust from around 10.5 to 13.5 volts. And we use that as the reference. And so instead of having a pot and the voltage divider, we use the pot to change the voltage. As long as the voltage going to the op amp is over 10 volts, it's fine for driving a FET. And so we use a voltage divider to divide that voltage in half, and so that's basically 6 volts. And you have a comparator input. We have a capacitor on the input to basically it creates a time delay and it filters out noise. And use a 4.7K resistor on the downside of that. On the upper side, you have to select this for the voltage you're going to work at. And so basically, for every 6 volts, it's 4.7K. There's a number of voltage divider programs on the internet that you can use to calculate out exactly. But if you center that voltage for this to be about 6 volts, then you'll have about plus or minus 10% range that you can adjust with the power supply. So this power supply works anywhere over 40 volts. It actually starts working about 30, and at 40 volts it's really safe. So most panels, you'll need at least 2 panels in series to heat water. You'll have more than enough voltage. So the solar power comes in here. It gets sensed at this comparator. So this is set at 6 volts. And whenever this voltage gets above 6 volts, this will turn on. So just remember, a positive voltage into plus gives you a positive voltage out. And this is a second buffer. I use that. These are very slow op amps, and this helps to filter out any noise. We drive a FET with a 330 ohm resistor. This can be anywhere from 100 ohms up to around 330. We have a high resistance here in order to create a slow turn on and turn off, as you saw in the video before. This doesn't make any noise because the transitions are so slow. And at high speed, that would be really a big problem because you get into transition heating on the FET. But because we're only running about 400 to 1,000 hertz, there aren't that many transitions, and it's just easier to get rid of the noise that way. You have a diode up here and a capacitor resistor down here. You can do either of these, or I generally don't even put them in because generally if you have a short heating element, there's not a lot of inductance to it. And most heating elements, and I highly suggest this with any water heater when using DC, you use one which is grounded. Believe it or not, UL allows water heaters, the outside metal sheath is just to protect the element. It's not grounded, it is floating. And it requires on the insulation between the nichrome wire and that outside sheath to limit current. UL does allow some leakage. So I suggest you use a water heater heating element which is not gray. Choose one that has a visible grounding to the mounting screw in, and that'll make sure you don't have any currents which would cause erosion of the water heater tank. But in having a closed loop like that, it's like a shorter loop on a transformer. Any noise that's generated in that coil is just grounded out. So noise really isn't a problem. You want a capacitor bank. I use like 6,000 microfarads for a 6 ohm load. So if you went down to half that resistance, 3 ohms, you'd want to double that capacitance to have a really good system. But in the video I showed you, I'm using a 470 microfarad. It's a very low ESR capacitor, but you can't guarantee that you'll have a low ESR capacitor. So as many as you can get. I always think that the world should be free with electronics. There's so much junk out there, old power supplies. If you get a bunch of old computer power supplies, they'll each have 2 high voltage capacitors in them. And I've made these with, close to a dozen capacitors. They're only about 220 or 330 microfarads, but you get a bunch of those in parallel and you'll have a low ESR, and they'll work. Like I say, put as many capacitors on as possible. That's the best thing to do. So like, you have the power supply, that takes care of a lot of problems, because early in the morning when the sun first comes up, that's when a lot of circuits will fail, because a lot of designers don't count on the voltage coming up really slowly, and you don't want to be operating this in a linear region. Basically, if you're driving a FET with under 5 volts, it's going to really heat up. So you want to stay away from that. And that's what, having a switching power supply that turns on at 30 volts, that'll give you a secure source. It'll just pop on. You'll have the voltage. And the nice thing about it is, a lot of times you'll be using a power meter. And if you're doing higher voltages, over 100 volts, that power meter may not accept being self-powered, from 120 volts. They may have an input coming into it for, 12 to 30 volts. So that power supply eliminates a lot of problems. And you only have this one IC to deal with. You can easily put those resistors on a perf board with this. You're just not dealing with that many resistors, and you're dealing with a single IC. If it blows up, pull it out, put a new one in. You can get 50 of these with sockets for about $7, so that's not a lot of money. Find some friends who want to do this. These make good cookers. If you want to do cooking from your solar panels, this is a great way to do it. You just got to remember, the sockets itself will have a little notch in the center, and the ICs will either have the dot or a little notch at one end. That signifies pin 1. So when you flip it over to wire it, it'll be basically clockwise, 1, 2, 3, 4, 5, 6, 7, 8, just going around in a circle. These pins, you can flip them one way or the other. So if you alternate them, you'll have a much easier job soldering, because your solder blobs won't jump over. Use a board like this with plated through holes. The ones that you see that are copper are just a foil on one side. The holes aren't plated through. Those foils will lift off easily. This is a much better board. So when you set this up initially, remember, this will switch at 6 volts. So when you're trying to debug this thing, all you really need is this power supply. And like I say, you can power that up with the panels, or you can connect it up right to 120 volts temporarily, just power your board with the 12 volts, and you can tie this point up to positive 12 volts, and it will turn on. If you apply 12 volts here, and this turns on, and that turns on, and the FET turns on, you know, that's your diagnosis. So it's fairly simple. You know, you're going to make some mistakes probably, but you'll learn something, and that's the important thing. You know, and I'm here to answer any questions for you. Just remember that you can use any kind of reference here, and later on I can show you how you can replace this 4.7K with a zener or a couple LEDs to create the reference, or you can use a string of diodes, and then you can have temperature compensation. If you run this temperature sensor outside with a little piece of metal on it that will heat up from the sun like the panels would, you'll have thermal tracking, and you won't need that much of an adjustment between summer and winter. So this is it. Any questions? I'm here to answer.